To begin, let's look into the semiconductor devices and scaling with the industrial approach. So this picture, you can see the classical or the textbook style CMOS transistor. So essentially, you have a gate overlapping with the source and drain contact. By tuning the voltage, you can accumulate the channel connecting source and drain. So that's how you have a transistor or trans resistor. So it's electrically tunable resistance. But however, if you look back into the 1990s, then the transistor is actually very different from the textbook style. So on top of the source and drain, you actually have an extension of the source drain with lower doping. You also have a hollow region with a reverse doping. All those things are needed to overcome the short channel effect. What does that mean? When you shrink the size of the when you shrink the size of the transistor, essentially the source and drain begin to merge. So to overcome the merging or the short channel effect, you need to play some clever tricks there. For the further improvement or the further downscaling of the transistor nanoscale into the 90 nanometer node, that kind of trick is not enough. Essentially, when you try to further scale down the gate dielectric or the gate capacitance, it's reached a limit. So you need to look into the other side of the formula. So you need to improve the mobility. The way to do that is to incorporate strain into the transistor model. So for P-type, typically people incorporate silicon germanium to incorporate the strain. And for the NMOS, people need to put another layer, typically silicon nitride layer, to introduce the strain. Okay, now in the years of 2007, people introduced idea of high K plus metal gate. Why is that? It's when you further shrink down the gate capacitance, you need to reduce the gate dielectric layer. To achieve that, or if the layer thickness is too thin, then the quantum tunneling event or the gate leakage current going to be too high. So people introduce high K metal, which essentially you can achieve very narrow effective oxide thickness with very big physical thickness. But however, due to high K is reacting with the polysilicon, so you have to use metal gate. But the metal gate is not so compatible with the high temperature processing, which essentially you need to implement the replacement gate. So that's why you have the high K metal gate and you have the replacement structure around it. And towards even further scaling, you need to have better control of the channel. So that's why you need to introduce the FinFET. Essentially, the currents flow inside the fins and you have the gate wrap around the fin to control the current. So the progress in the CMOS technology through scaling is actually the PPAC. Those are the 4 important factors. The first is the power. For each generation, there's going to be 25% increase in the power performance. Sorry, in the frequency performance or in the operation speed. Then a 20% reduction in the power consumption. And follow the Moore's law is essentially 50% size reduction. And in total, it's going to bring roughly 15% in the cost reduction. And that cycle repeat every 2 to 3 years. And not just the transistor size, the size of the wafer also increases with time. So essentially, starting from the small wafer, nowadays, most of the commercial transistors are processed on the 300 millimeter wafer. Okay, if we try to put everything together, back in the 60s, up to now, there's actually a lot of innovation that drives the downscaling of the transistor scale. So, but on top of that, there's also many options that can still be investigated. Essentially, that's a combination of the new material and also architecture. And on top of that, there's a system and the circuit level, the circuit level development. So that's also a summary page about the scaling trend. So down to the 130 nanometer, the plant structure, and then that's the introduction of the high K and the strain, the high K down to the 45. And around 20, that's the introduction of the FinFET. And for the 14 nanometer, that's even narrower and high aspect fins. And if we want to scale forward, that's all around gate structure or the nanowire. So across the map, there's a lithography driven or the tool driven, and also the material innovation that is needed to improve the performance. And finally, that's the device architecture, bring more control. And so here, that's also a deeper look into the transistor performance. So on the x-axis, you can see that's the length of the transistor. You can also see that scaling of the transistor. Towards the left part, that means smaller transistor. But when you move But when you move towards the left side, what we see, the power delivery should also be reduced. Needed for the power efficiency. That's also something benefit. The threshold would also decrease, but in the meantime, the threshold voltage, the oxide thickness will also decrease. But the drawback is really towards the smaller transistor, the reliability is a big problem. And the other way to look into that is basically the transistor, you can think it as a switch. For ideal switch, you have on state, you have off state. But in the transition, you want it to be a perfect sharp transition. But however, when you have a planar transistor, it may not be very sharp. And that is limited by the channel control. So to improve the channel control, you can actually use a FinFET structure. So you can see here, the on-off control is much better. To improve that further, you need gate-all-around. That's essentially the nanowire FinFET. But in the meantime, from this picture, you can already know, when you reduce the transistor dimension, you also need multiple of the channels to maintain the high current through the transistor, which is also shown here. So basically, when you reduce the size, the reliability is a problem. Okay, so that's actually the summary of development trend for the fin and also the nanowire. So when people begin, they begin with tapered fin, which is around with 7 to 10 nanometer. But for better control, then the fin actually gets taller and also narrower. So you can maintain the high current, but with better control. And then that's the ultra thin fin. And for the ultimate control, you can have the gate-all-around structure. So basically, the introduction of the gate-all-around nanowire is crucial for improve the device and the electric performance beyond the 5 nanometer node. And when we are talking about those 7 nanometer, 5 nanometer, or 14 nanometer, those things actually they follow the original prediction of the Moore's law. But because the introduction of the fin and also the nanowire, those numbers may not be actually correlated to the device geometry. So the real interesting parameter is actually look into the gate pitch times the metal pitch. Those are the things that matters. And then to characterize the device performance, it's worth to look into the frequency or the performance on the x-axis versus the power on the right axis. Crucially, people expect we operate in this region. So to really go in there, we need to have narrow fins, taller fins, and for better control, we need to go to gate-all-around. But when we go to gate-all-around, that's in the nanowire, then the area is small. So that's something called nanosheet. So you can also think or envision as elongated nanowire. So you can also maintain high current flow through, but also gate-all-around structure. So here, that's a summary page. And for the standard development of the CMOS technology, so the black line, that's the prediction by the Moore's law. On the x-axis is the performance of the transistor or the transistor per dollar. On the y-axis, that's the time. So on the planar region or the planar transistor region, it still more or less follows the Moore's law. But when we are actually hitting the limit of different design and also material prospecting, we need to look into different structure. So that's where the fin actually came into the picture. However, as I explained earlier, when you have a transistor, it actually incorporates multiple fins, essentially to have high current flow through. But for the downscaling requirement, you also need to reduce the number of fins. Okay, so how can we achieve that? Well, by material optimization and also clever structure design. And for the structure that even goes beyond, we can expect some larger deviation of the real performance. And for that, it's really the gate-all-around structure and more innovations. But the focus of the technology innovation is really to scale the device and also wares, but to really catch up or keep to further increase the performance and also to further increase the device scaling, we also look into how to scale the basic logic cells and also how to scale the subsystem functions.